Alright, so this is 2011 Form B, question 1. Again, another calculator problem, so we'll be taking care of that today. So it says a cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. The can is initially empty, and rain enters the can during a 60-day period. The height of the water is modeled by the function s, where s of t is measured in millimeters and t is measured in days from 0 to 60. The rate at which the height of the water is rising in the can is given by this s prime function. So again, we're given a rate right here. Okay, so just keep that in mind. This is a rate. And it says, according to the model, what is the height of water at the end of the can at the 60-day period? Well, before I even answer that problem, I'm going to punch this thing into the calculator, which is what I have. Okay? And then, I've already entered it in, so if you need to pause and enter this into the calculator, I'm also going to switch the window to go from 0, not to 6 anymore, but 0 to 60. And that gives me that right there. Okay? Just in case I need to find any x-intercepts, which clearly there aren't any, but that's okay. It should make sense, right? If we don't dump any of the water out, the water level should always be, going up. Okay, so if I wanted to find out how much water accumulated in that can over the 6-day period, well, I'd want to just use integration for that, right? So I'm going to integrate this function here on 0 to 60. So let's do that. So shift plus 0 to 60 of, this is f1 for me now, f1 of x dx. And that's what I got, this 171 number. So let's go ahead and enter that in. So this is relatively easy. Just put it over here. So A, if I was to integrate from 0 to 60 of s prime of t dt, I would get 171.8134728. Does it ask me for any units of measure or anything like that? It doesn't say anything. It's not indicating. It says, what is the height in the can? And that's all I need. Okay, cool. So I think I'm good with that. Cool. So a pretty straightforward kind of problem right there. Part A. Part B. According to the model, what is the average rate of change in the height of the water over the 60-day period? Show the computations that lead to your answer. Indicate units of measure. Okay. I often ask, what's the highest level of math you need to solve a question, to solve a problem that talks about average rate of change? And in this case, the lowest level of math you need, the highest level of math you need to do this is not Algebra 1. It's actually calculus. This time, in order to find the average rate of change, I'm actually going to use integration. Now, why is that? Why don't I do s prime of 60 minus s prime of 0 over 60 minus 0? I'm not going to use y2 minus y1 over x2 minus x1 because if I derive, right, or get an average slope, an average rate of change of a rate that's already there, I'm finding the average rate of that rate. I don't want that. I want to know where this rate was averaged out. So, kind of like when we find average velocity, we integrate the velocity function with the 1 over b minus a. I'm going to do the exact same thing here. So I'm going to integrate s prime of t dt on 0 to 60 with a 1 over 60 on the outside. Okay? So let's do it in the calculator, because that's easier. So one of the wonderful things about this calculator is I can just do this, and I can multiply it by 1 over 60. Now, some of you guys are faster than me. You could have just as soon then said, wait a second, just take your last answer and divide it by 60. That would have worked too. That would have been okay. Boom. So the average rate of change is this 2.86 number. So I'm going to go and write that down. This 2.86 number. And they want me to indicate units of measure. So this is going to be millimeters per day. right? Because we're integrating, we are getting a rate out, right? So the average rate is millimeters per day. Do not mess up the units, otherwise you could end up getting some points that could be lost in the abyss. We do not want that. Okay, let's take a look at part C. Part C says, assuming no evaporation occurs, at what rate is the volume of water in the can changing at time t equals 7? This could be an indicate units of measure. So this could actually be a really complicated problem, except if you know what the volume of a can is, it's V equals pi r squared h. Now, one of the wonderful consequences, I suppose, of this thing being a cylindrical can is that, well, pi is not a variable, but it never is. And r is also not a variable, because a cylindrical can, it's not like a cone, right? It's a can. So the radius is going to be staying constant the entire time. And the radius is told to be 10 millimeters. So it's just pi times 10 squared. And h is given by, hey, wait, isn't the rate at which height is changing given by this function here? So isn't it just s prime of t, right? That's going to be, or rather, not even s prime of t yet, I'm jumping the gun here. The height is really just s of t at any given time, right? Now, if I go and derive this thing, now I'm going to get v prime equaling 100 pi, and that's where the s prime of t comes in. But I don't want that value anywhere. I want to know that value at, at 7 days in. So let's do it. So I'm going to find out what f1 of 7 is. And I'm going to multiply that by 100 pi. And what I get is this 602 number. So 602.218. .218. Now, in this case, since it's indicate units of measure, this will be millimeters cubed per day, right? Because we're studying volume now. Let me go ahead and clean this up, and we'll go ahead and get started with part D. The last part, part D, is it seems complicated, but it's actually not terrible. It says, during the same 60-day period, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. The height of the water in the can in Monsoon Mountain is modeled by the function m, where m of t is equal to that polynomial. The height is measured in millimeters, blah, blah, blah. It says, let d of t equal m prime minus s prime. Okay, in other words, d is the two rates being subtracted. And it says, apply the intermediate value theorem to function d to show that, to justify that there exists a time at which the heights of the water in the two cans are changing at the same rate. Okay, so these are often the questions where realistically you could just answer it in a couple words and say, okay, yes, they do. But unfortunately they're asking you to justify. So they're kind of baiting you in a good way, because they're saying apply the intermediate value theorem to show that they do change at the same rate. So they're already telling you, yes, these two cans do change at the same rate. But we have to now prove that. How do we do that? Well, if this statement was true, that means that d of t would have to equal 0 somewhere. Well, what does that have to do with anything? Well, what that means is that because d of t is equal to m prime minus s prime, and because if I assume that d of t equals 0 at some point, that is to say that m prime minus s prime would have to equal 0, right? So it's like a leads to b, b leads to c, a leads to c. And that, in and of itself, means that if I added the s prime to both sides, that means that the two rates would eventually would have to be the same at some point. So how do I prove this? Well, first thing I'm going to do is I'm going to find out what d of 0 is. Well, what's d of 0? Well, that would be m prime of 0 minus s prime of 0? Okay, well, let's find out what those are. I'm going to go and plug m into the calculator here. So I've got m, that's my f2, hit enter, cool. And we're going to tab out of this thing. So if I wanted to find m prime of 0, I'm going to use that function derivative at a point. Value is 0. And I'm going to look up f2 of x. Boom. That's 33 over 40. I want to get that into a decimal, please. Okay, that's 0.825. So I know that this is. I'm going to go inside. I'm going to go side by side these two. Split screen them like they do in 24. Okay, so I know that this value is 0.825. Well, then let's find out what s prime of 0 is. Well, s prime of 0 happens if I look at f1 of 0. That's 1.5. Okay, cool. So that's minus 1.5. So now what's 8.25 minus that number? So let's take these two numbers and subtract them. I think some of you probably already know where this is going. So that's negative 0.675. So that's negative 0.675. In other words, this number is below the x-axis. In other words, this number is less than 0. I think you guys kind of know where this is going, right? Because now I'm going to evaluate, well, what is d of 60? Well, that's m prime of 60 minus s prime of 60. Well, how do I get m prime of 60? Well, that is going to be, again, my good old friend calculator here, derivative at a point. 60. Now, again, I'm going to go ahead and evaluate f2, right? Whoops, not f at, f2 of x. And what does that give me? Well, that's going to give me 72.825. So 72.825 minus, well, what's s of 60? Well, that happens if I look at f1 of 60. That's 3.44 blah, blah, blah. 3.447695 blah, blah, blah. So if I subtract those two values together, 72.825 minus, I'll go and just do minus answer, I get 69 point blah, blah, blah. 69.377. So, what does this mean? Well, I've got a continuous function that is at one point below the x-axis and at one point above the x-axis. So, how can I use IVT to justify that? Well, here's how I do it. Before I get started with anything else, I have to establish that d of t is continuous on 0 to 60. You always have to establish the continuity and the differentiability of your functions, especially if you're using MVT. For IVT, you can just use continuity, so that's what I'm going to do. So d of t is continuous on 0 to 60. And now you can say by IVT, there exists a time between between 0 and 60 where m prime of t minus s prime of t will equal 0, and therefore m prime of t will equal s prime of t. Done. That's all there is to it. So again, seemingly complicated because there's a lot of words here, but it's not terrible, I don't think. So anyway, that's how you do it, and we'll see you in the next FRQ.